Hi, this is Mark Weitzman. Welcome to my channel, Theoretical Physics with Mark Weitzman on YouTube. Today I had a request to explain the symmetry factors for quantum field theory diagrams, and especially with reference to Chapter 9 in Mark Symmetry's book. And I was very honest, and I said that while I understand where they come from and where they are, I have a great deal of difficulty in calculating in understanding in getting the right symmetry factor for a complicated diagram. For a non-complicated diagram, I can reason it out. But what I mentioned to the student was that one can always do an explicit calculation, and so this is what I want to do in this video. Um, And so this is part of lesson 9, the path integral for interacting field theory, a deep dive, explicit calculation of a symmetry factor for a phi cubed diagram. So the theory we're working in is phi cubed, and the reference is Szymanski, chapter 9. For this video, you really only need to be familiar with pages 60 to 61 and figure 9.3, as well as equation 9.11. And I'll explain how they figure this out. So we start on page 60. Szymanski and all books do this. They give sort of like a dictionary. Between the actual Taylor expansions or perturbation expansion and the I'll put a quote, Feynman diagrams. The purpose of the diagrams is to give you a way to do it automatically and not worry about all the numerical factors and so on. The idea is to do it once, work it out, and then you can always just draw a diagram and give the perturbation expansion. So I'm going to turn up the volume a little bit. I didn't have it that high. Sorry about that. So the dual perturbation expansion perturbation expansion is given in equation 9.11, and I will write it down again. He has Z1J is proportional to. Now this proportionality has nothing to do with the symmetry factors. What it has to do with is he's eventually going to set it equal to 1 when the sources are 0, and this will take out vacuum diagrams. So that's a whole nother issue. So that's why he has a proportional sign here, but don't worry about that. Think of this as an equality sign for the purposes of this video. So he has the sum from v equals 0 to infinity, 1 over v factorial, and v will actually is the vertices. Zg is a renormalization factor. G is the actual coupling strength of the theory. The integral of d4x 1 over I del jx. This is a functional derivative, and this thing is cubed, and this is to the power of v. times the sum from p equals 0 to infinity, 1 over p factorial, I over 2, integral d4y, d4z, jy, this is the Feynman propagator, del y minus z, jz. So that's the actual formula, and you know where he gets that you can read in the book in that chapter. And the dictionary that he has is on a diagram. If you have like a point X with a line, it's usually straight, but it doesn't have to be, connected to a point Y, this stands for the expression one over I Feynman propagator del x minus y. The Feynman propagator is even, so del x minus y is del y minus x. Doesn't matter what order you do these things. Then when you have a source is like a big dot, and a line connected to it, and the source is, let's say, at position x, and this is I, the integral of d4x jx. And then when you have the vertex, that's just three lines meeting at a point x, and this is I z g g, the integral of d4x. So figure 9.3 the diagram is a very simple diagram. It's that. Now, the reason why I'm working with a very simple diagram is that this would be very, very complicated and a very long calculation if I were to try and do the diagrams that some of the other ones that he shows in the chapter. The ones where the symmetry factor is kind of like hard to reason out. So the thing is, I just want to illustrate that it does work. Even for this one, it will be like a page calculation. You can use software. You can use, Maple or Mathematica and program some expressions with functional derivatives, and hopefully it will work out right. For this one, it's easy to do by hand. So this diagram has E equal 1. E stands for, so that's like one external source, which is the blob. As V equal 1, there's one vertex. That's where, like I said, the lines don't have to be straight, but you can see we have one line, two line, and three lines all meet at a point here. So that's one vertex, and it has P equal 2. P stands for propagators, Feynman propagators, and there are two propagators. There's the propagator between the source and the point, and then there's one propagator where it goes all around and connects with itself. So this is the diagram I want to work with. It satisfies, there's an equation that Snecker gives, E equal 2p minus 3v. And the claim is, there's two claims that if you look at figure 9.3, one is there's only one, so claim 1 is there is only one connected diagram with with E equal 1, V equal 1, P equal 2. And then the second claim is that the symmetry factor is 2. And when you work with realistic theories, as I think one textbook, it might be Ramon, but I can't remember exactly. One of my textbooks kind of say that, or at least years ago, for the most part, you're never going to see a symmetry factor higher than 2. Basically, you'll have a second order diagram and maybe the symmetry factor will be 2. When you go beyond that, when the symmetry factors get larger than that, you're working with, third, fourth, fifth order perturbation diagrams, which are extremely difficult to calculate. So nowadays we can calculate them with computers and so on, but they're still very difficult. For a textbook, you're not going to see a symmetry factor higher than 2 that you actually calculate the diagram if you're working with a realistic theory. So now one can reason about switching the propagators here, and that's where the symmetry factor of 2 comes from. First thing, what does the symmetry factor 2 mean? What it means is that if I were to use this dictionary to translate this diagram, would that expression, that equation, would that be the same as I get from the Taylor expansion? And the answer is sometimes yes, when the symmetry factor is 1. In other words, when there is no symmetry factor, the answer is yes. But when there's a symmetry factor of 2, it means that you have to divide the expression you get from the dictionary, from the diagram, divide by 2 to get the expression from the Taylor expansion. And that is what we're going to show. So let me start. First, let's do the dictionary for the diagram. For the diagram, figure 9.3, which I show above. This is it. So I'll put points on it now. So I'll have a source x goes to a point y, and then we have a propagator that creation of a particle, annihilation of a particle. Basically 3 particles are meeting at this point, and how you think of them doesn't really matter. There's no difference between particles and antiparticles. So let's write down the dictionary for this diagram. So using what we have above, first we'll start with the source. We're going to have an I term, the integral of d4x, j of x, and then we're going to have an integral of, we're going to integrate over the point y as well, d4y. The propagator was between the source and the vertex, del x minus y over I. And then we have the vertex factor, which is I zg g del y minus y over I. Now, this seems a little funny, and we'll talk about renormalization later and everything, but we're not going to write del y minus y, we're just going to write del 0. That's what it is. It might be infinite and everything, but we're not worried about that right now. So, as you can see, the i's all cancel. So this is just equal to zg g, the integral d4x d4y jx del x minus y del 0. So this is our goal, to get a formula like this. And when I said before that the claim was that there's only one connected diagram, if we were to end up getting like 2 separate formulas when we do the Taylor expansion, one formula could correspond to a certain connected diagram, and the other formula could correspond to a different connected diagram. So we'll find out that we get only one diagram that's connected, and we'll find out that it's not exactly this expression. It's going to be this expression divided by 2. And that calculates the symmetry factor. Okay, so now the dual Taylor expansion, when we substitute in this beautiful expression over here, which I'll just put star, when we substitute in star, we're choosing here, we've already made our choice that v equal 1 and p equal 2. So we just take the term which has v equal 1 and p equal 2. E is not an independent variable. This is only 2 independent variables. So let's, so we have 1 over 1 factorial I zgg over 6, the integral of d4x 1 over I, functional derivative with respect to j of x, cubed, so we're going to apply it 3 times, 1 over 2 factorial I over 2, integral d4y d4z jy del y minus z del y minus z jz, and this propagated because there's 2 of them, it gets squared. So writing this out, first thing you'll notice that we have 1 I in the numerator, 3 I's in the denominator, 2 I's in the numerator, so the I's all cancel. And so we get 1/12. We have the 1/6 factor, and we have the 1/2 factor. I'm going to leave this half factor here with the 2 propagators for a reason which is pretty obvious, as you'll see. So we have 1 over 12 zgg integral of d4x. Now I'm going to explicitly write this out so that we understand that this is just the third derivative. You know, we're going to apply 3 derivatives of the sources all at the same point. Now we're going to apply it to 1/2 the integral of d4y d4z jy del y minus z jz. And then this factor occurs twice because it's squared, but we have to use other variables when we represent it the second time. So this is times 1/2, I'm going to use primes now, the integral of d4y prime d4z prime jy prime del y prime minus z prime jz prime. Okay, so the idea is just take one derivative, functional derivative, simplify it if you can, do it again and do it again and see what we get. Okay, so this is equal to 1/12 zgg integral d4x del jx del jx Now, here's what we're going to do. So when we take the functional derivative, we'll do it first of the first term, and as the product rule still applies, product rule in calculus for derivatives still applies. We're going to take the first term, multiply it by the second term. Then we're going to take the second term and multiply it by the first term. Now when we take the functional derivative of the first term, we apply it, it's going to, again, we have a product here, so it applies in two places. When we take del y del jx, we get a delta function, delta y minus x. We then integrate over y, which simply sets y equal to x. So we end up getting the integral of d4z del x minus z jz. Now, for the other term, you might think I left out the half, but I didn't. When we take the functional derivative of jz, we get delta z minus x. We integrate over z, and that substitutes, so we get Feynman propagator y minus x integral d4y jy. But that's the same thing as the term I already written down here. It's just substituting y, changing variables y for z. It's symmetric. So whenever you have this 1/2 here and you take these two derivatives twice, they cancel. And this is multiplied times 1/2 this expression. I'm going painfully slow here because I know some people haven't seen these functional derivatives before. Now we need to do the second term. So we write down the first term, 1/2 the integral of d4y. And it should be obvious, the first term and the second term are the same thing. They're just written with different variables. So I'm just going to get twice this expression, but I'll just do it explicitly. d4y, d4z, jy, del y minus z, jz, times. And now, when I do take the functional derivative of these two terms, it's exactly what I got the first time, except I have prime variables. So I'll just write it down. d4z prime, del x minus z prime, jz prime. Now you can see that these two terms are exactly the same. Just where you have a y, exchange y with y prime and z with z prime, and you can see that these two terms are the same. So we end up getting 1/12 zgg integral d4x del jx del jx times this expression, which is integral d4z del x minus z jz times the integral d4. I'm going to leave it at y prime because there's a z variable here and I don't want to have a conflict. You got to keep the variables in the different integrals as different. jy prime, Feynman propagator y prime minus z prime, jz prime. Okay. So we've taken one derivative. Now we take one more derivative. 1/12 zgg integral d4x del jx. Okay, so now I've got, it's the product rule. This time they're not the same. When we take the functional derivative of jz with respect to x, we get del x minus z, small del, Dirac delta, x minus z. We integrate over z, it sets z to x, so we get Feynman propagator x minus x. So that's just Feynman propagator 0 times. Now I'm going to change the primes back, so I'm done with the prime variables here. The integral of d4y d4z jy del y minus z jz plus, now I have to do the second term, so I have plus the integral of d4z del x minus z, this is the first term above, jz times. Now, when we take the functional derivative of this, it's the same old thing. We're going to get exactly what we got over here. Same thing. So I'm just going to write it down as there's no 1/2 factor here. That's the difference. So we're going to get a 2. As a matter of fact, I think I made a mistake. No, I got it right. Plus that times 2 times the integral of d4y. Again, I can change the variables because I'm only going to have y here. jy del y minus x. Okay. One more derivative to go. So this is equal to 1/12 zgg integral d4x. Now let's see what we got here. We got, again, taking the derivative of this standard term, which we always get, it gives us a factor of 2. First I have del 0. There's a factor of 2 because I have 2 terms and I'm going to differentiate each one. And I'm going to get jz, sorry, 2 times the integral jz del x minus z plus, now here again, okay, so now I'm differentiating down here. The first term is going to let me think this out. When I differentiate the first term, I'm going to get a Dirac delta z minus x. So I'm going to just get left with a factor of del 0, one factor, del 0, and I know I'm doing this wrong. I got my factors wrong, even though I wrote this out. Maybe not. Let's see. Okay, so this over here is going to give me del 0 times 2 del 0, the integral of d4y jy del y minus x. I left out the d4z over here. And then finally I have also this term times the functional derivative of this term. So now I get 2 plus 2, the integral of d4z del x minus z jz. When I take the functional derivative of the last term, again, it gives me a Dirac delta of y minus x, and then it replaces y by x, and I get del 0. So I get times del 0. So if you look at this now, they're all the same term. They're all the integral of a variable, the functional derivative of the variable, and del x minus z. Here I use y, but I can change y to z. And so I get, so this ends up equaling 1/12 ZGG integral d4x del 0, the integral of d4y jy del y minus x. Okay. So this is our, I left out the 6. 2 and 2 is 6. So it's 6/12. So this is equal to 1/2. Now let's change variables from y. Just rename x to y and y to x. So I get 1/2 ZGG integral d4y d4x del 0 jx del x minus y. And if you go back to what we calculated earlier from the diagram, it's the exact same thing, except that there's a factor of 1/2. So we've calculated this as the symmetry factor. We need to divide the diagram result. Divide diagram dictionary by 2. That's what the symmetry factor is. So you can do this for more complicated diagrams, or you can do the reasoning that Shineki does in the chapter. Like I said, the reasoning, when you get more complicated diagrams, it gets more and more convoluted and easier to make a mistake, and whether you get the right symmetry factor depends on how good you are in combinatorics. So I will leave it there. Thank you for watching, and I'll be back with some more videos in version 2 for the lessons 6 to 9. Thank you very much. Bye-bye.